So thank you. Yeah, so this talk is a little different, and it's just giving context for a pretty recent idea, and seeing how it could be implemented for multiple missions at the South Pole. So true polar wander is how the spin axis of the moon or the Earth moves around with respect to the crust, right? So it's not the same as a change in obliquity, but both of them are important to the long-term survival of volatiles at the poles. What's especially important about true polar wander is that it can be linked to thermal evolution, large-scale, long-lived geophysical processes that are hard to pin down. And so having an accurate history or a better constrained history to put on at the moon would have implications for a lot of Artemis 3 science efficient team science goal or adjacent goals. So the question that we set out here was, can the Artemis campaign as a whole, starting with Artemis 3, address true polar wander history of the moon? And so one of the issues is that many different techniques have been used from geophysical arguments to geomagnetic measurements to try to constrain where the Paleopole was. But as you can see from this image that was compiled by Mazarico in 2016, there's very large discrepancies between different measurements and no clear right solution at this time. As I was mentioning, some of the importance of true polar wander is that it could have a large effect on survival of volatiles at the poles. Here in this paper by Mazarico in 2016, it was proposed that the PKT region formation due to mantle convection could have changed the polar axis by as much as 60 degrees over the history of the moon. And so bringing further evidence of such a large polar wander would be very interesting. Also recently, work with colleagues looked at the effect of impact craters. So before that study, only the largest basin had been considered in changes of the moment of inertia of the moon, which leads to that reorientation and true polar wander. And so here we had looked at most craters on the moon and having an effect. And so from that we found that true polar wander could be up to 10 degrees in latitude from those effects. I also didn't mention that the obliquity change is also expected from Earth-Moon distance evolution. And so that is pretty limited to a few degrees over the past 3 billion years. And so depending on which scenario you have, if you have that huge mantle convection-driven true polar wander, obliquity-driven volatile disturbance would be small. If you are in this scenario, then they could be on par with each other. So again, the point here is to say, how can we put a constraint in the deep past of where the Paleopole was? And so one of the things is that the PSR age prediction is different for every of those models, right? So right now, those are more forward models. We have a predicted history of true polar wander. We have a predicted history of obliquity. And from those, we can compute the age of the PSR with those models. But the point is, if we go down to the ground and actually can make measurement of PSR age, that would be very interesting to constrain those models of both obliquity change and true polar wander history. So that's a big premise here. And I'm not going to go into how we could measure that. I would actually be very interested in getting feedback from some of you who are a lot more knowledgeable about geochemistry, for example, about how that could be done. So here I'm going to assume that when we go to one of those regions and a site and explore one of the PSRs, we could get a point measurement of whether or not that place was a cold trap at some point in the past. So here in what I'm going to show, the examples I'm going to show, I'm going to assume that all of those past are the same date, but it doesn't have to be. That would complicate a little bit the analysis, but it's not a barrier to that. So to illustrate that, right, why would a spin axis change relative to the crust, change stability of the PSRs? Here's an example where we have the current pole in the blue, at the blue point in the South Pole, and we have a crater nearby that is a permanent shadow. As we move the Paleopole position, that crater could still host a PSR, and so be a long-lived cold trap. On the other hand, if you move the other way, for example, maybe only part of that permanent shadow region currently would have been also a cold trap in the past. And if you move further out, then maybe that's a completely warmer region, low latitude in that configuration, and not an old PSR. So notionally, you could see that there is probably like a boundary where you can define that if you're on a certain side, then you do not expect that current PSR to have been a PSR in the past. And if the Paleopole was the other side of that line, maybe you would expect it to have been a Paleo PSR. So with that in mind, here this is showing the expectations for one of the PSRs near in the connecting ridge region. So that one is very close to the pole. And so not very surprisingly, what you see is that as you move the Paleopole away from the current South Pole, you decrease the area that is expected to be in permanent shadow. So those shows contours of, compared to current area, how much area was in permanent shadow. And so this map here, what you see spatially now, is you can imagine that's where the Paleopole was, right? So if the Paleopole was near the top here, then you would have almost, you would have no PSR. If it had not moved much and the latitude of the Paleopole was close to the current South Pole, then you probably would retain most of the PSR. So again, that one is pretty close to the South Pole, so pretty symmetric. But what we did was select one PSR for each of the regions and compute similar maps. So here, this is a context map that has been shown several times already. And so as I was saying, for each of those, I selected one PSR, which is in the range of about 1 kilometer in size. So not too small, but not the largest either. And so now for each of those PSR, I run about 4,000 simulations for different Paleopole positions in the 80 to 90 latitude range. And this is what I get. So this is the same type of maps as I shown a couple slides ago. You can recognize the one I was showing here for the connecting ridge PSR, but now that's all of them. And what you could see, as expected, is that you have a bit of a latitudinal trend and a longitudinal trend, right? So depending if you go to a PSR which is far away from the pole or close to the pole, you're more or less symmetric. And as you move in longitude, those clock a little differently. And so the idea now is that if we can go to several of those regions, several sites at the South Pole, we can, little by little constrain the existence of paleo PSRs and thus the location of paleopoles. So here, this is one example from 4 sites. So imagining that we have 4 Artemis missions, or it doesn't have to be exactly Artemis, but depending on the in situ measurement technique or sample return measurements, that may have to be. Imagining, for example, that we find that the paleo PSR at the connecting ridge did not exist. So that's red here. And we find, for example, at those 2 other sites that we go, that those actually were still cold traps a long time ago. And then this one, Haworth, also not a PSR. So that would give us this presumed, most likely Paleopole position, which would be sort of a little bit on the far side in that region in yellow. And so now, depending, if we have another example, another sort of set of measurements we get back, that would define another region and another example again, right? So depending what we get in terms of actual measurements from the ground, that will define where the most likely paleopoles were. And so we haven't done that yet, but one of the next steps would be to see which set of Artemis regions would be most sensitive to paleopole position. So, excuse me. So in summary, this idea still needs to be developed, but I'll be happy to to get feedback. And please, I'll take questions in the chat, I guess. Sorry. Thank you.
Thank you, Erwan. All right, so at this time, we have several minutes left for Erwan's talk specifically, and then also 10 minutes open for general discussion. So if anybody wants to ask Erwan a question, please do that now. I actually have a question, which is, I think maybe to think of the analysis in the opposite way, in that if you were interested in understanding which regions had PSRs in the past, does that like eliminate any from potential for interest in a present day analysis?
Yeah, so it depends a bit on how far back you go, because as you go, maybe I should go back to this movie I was playing. depending on how you go, the obliquity becomes, I forgot to mention here in the left, right? This movie also takes into account obliquity changes. And so you can see that, the deeper PSRs, the deeper craters, Shackleton is one of the longest lived. If you go past 3 billion years, a lot of them shrink pretty rapidly. And again, that's with one specific model of true polar wonder and one model of obliquity change. So, from the previous slides, you can see there's a lot of differences in measurements of Paleopole locations. So I think, that's why I was going the other way. Is like we have so many different publications, published, work that gives pretty different true polar wonder predictions that it would be great to get actual, data on at least placing it in certain latitude and longitude range.
Great, thank you. Question in the chat. What do you think would be observational evidence for a paleo PSR? Ground ice at a particular depth or something else?
Yes. So thank you. Yes. So I come more from the geophysical side, and so I would think that potentially, right, if you can find in cores evidence for ice, and with ejecta you could date it, that would be probably the best way. But I'm also wondering if there could be any, isotopic measurements that could be done. I'm not totally sure on that. But dating sequences of ejecta is probably the most likely, billion to 3 billion year timescale constraint, I would guess.
All right, thank you.